question for you guys to talk to each other about before we get started. While I get my markers out, let's say. Here's the question. Are the trig functions one-to-one? And if they are not, what do we do about it? Give you our definitions of the inverse trig functions, all right? So maybe if I start with 457 here and talk about what do I mean by the inverse sine? Let's do that first, okay? So, and we want to talk about restricting the domain, okay? Y equals, sometimes we'll write arc sine of x, or we can say y equals the inverse sine of x, right? These are equivalent, okay? So we talk about inverse trig functions, and this is section 7.5. These mean a couple of things. These mean, first of all, that the sine of y is equal to what? X. And there's one other important thing here. Y is between two values, okay? Y has to be between two values here. So that's the question, which one is it, right? Is it 0 to pi or negative pi over 2 to pi over 2? For the arc sine, it's negative pi over 2 to pi over 2, okay? But you may not have all those memorized, and in some sense you don't need to. I mean, remember the question I just asked. I said, are the trig functions one-to-one? And the answer was no. And that goes for any trig function, right? So you could argue that initially a trig function won't have an inverse because it doesn't pass the horizontal line test, right? If I graph the sine function, let me do that. So if I graph, you know, y equals sine of x, well, let's see, that looks kind of like this. It goes through 0, 0. It's an odd function, right? And so you have to restrict the domain if you want to get an inverse. But you also want to get the full range of values that one could possibly have for the sine. And so what we do is we go from here, this minimum value of the sine, to this maximum value of the sine right here, right? If I choose the angles from negative pi over 2 comma negative 1, and here I have pi over 2 comma 1, that's a nice choice because I get the full range of values from negative 1 to 1. It's continuous, and so that's what we choose to do when we want to define the inverse sine, okay? So again, here's the sine function. Remember what the inverse sine means. It means you switch x and y, right? X equals the sine of y, or y is the inverse sine of x, okay? This will have a graph which is the reflection of that pink. Okay? This is how inverses work. So, again, the big theorem was that, hey, if I have a point on my function, y equals sine of x, I'm going to have a corresponding point on the inverse graph. So let's graph those 2 points. So let's see, instead of pi over 2 comma 1, we're going to have 1 comma pi over 2. And instead of negative pi over 2 negative 1, we're going to have negative 1 negative pi over 2. And it's still going to go through 0, 0. And because of it's a reflection, it's going to look more like this. because if I continued the wave, it would go up the y-axis. Okay, so there's a picture of the inverse sine of x right there. So are the trig functions one-to-one? No. So we restrict the domain. And this is where it's useful to know what the ranges are for the inverse trig functions, right? Because we restrict the domain of the original function, of the trig function. And so what we did was we said negative pi over 2 less than or equal to x less than or equal to pi over 2. And I guess what I should say is this becomes the range of the inverse trig function. Okay? And again, what's the range of this inverse trig function? Well, I said that up above. I said from negative pi over 2 to pi over 2. Okay? So again, on page 457, they list this fact. But on the other page, 460, they give you secant, cosecant, tangent, and cotangent, right? Well, inverse functions for each of those. And so maybe a quick peek at those. The other trig functions, they say tangent, negative pi over 2 to pi over 2, cotangent 0 to pi, secant 0 to pi, cosecant negative pi over 2 to pi over 2. I have to warn you guys, these, for the other trig functions, they're not always agreed upon. You can pick up a different calculus book, and they might have a different domain for some of these. Okay? A different range of the inverse trig function. And so that's kind of interesting. But it's a little beyond what I want to do. I guess the basic idea we know is that as long as it's one-to-one, there exists an inverse, and you want to hit the full range of values. Okay? And then what we're going to do is we're going to be doing problems that kind of use the ideas, you know. So here's a simple problem, right? The arc sine of the sine of 5 pi over 6. Let's compute that. But the answer is not 5 pi over 6, and that's my point for putting it up there.
That's right. It's,
why is it? Matter of fact, it can't be 5 pi over 6, right? Right. So look at what we just wrote down. We said this becomes the range of the inverse trig function. Again, the range of arc sine of x is negative pi over 2 to pi over 2 inclusive. So I'll put the brackets. That's the range, right? So when I say, okay, guys, problem, let's simplify arc sine of sine of, what did I do, 5 pi over 6? Okay. 5 pi over 6, it can't be 5 pi over 6 because the arc sine doesn't include 5 pi over 6 in its range. Okay? And so to avoid the difficulty, what I recommend you do, okay, is anytime in calculus that you have an inverse trig function, let's choose theta or some Greek letter and let that stand for the inverse trig function. Because if you think about when you learn trigonometry, right? Go back to sine. If I write sine of y equals x, y is an angle, you could say, right? A certain number of rotations. So in the inverse trig function, we switched input and output. Y is going to be an angle. The output is an angle. And if I understand that, what I'll do for a problem like this is I'm going to say, and this strategy helps throughout calculus, let theta equal the arc sine of the sine of 5 pi over 6. Theta is going to be the arc sine. And as soon as I write that, I can automatically write the next line. I can say the sine of theta is equal to the sine of 5 pi over 6. You can say, if I have theta is the inverse sine, that means the sine of theta is equal to something. In particular, whatever's in here. Let me go back to the top and see. You can see that in action again. I wrote y is the arc sine of x, so immediately I said that means that the sine of y is x. Right? And I need to know the range. So I guess the and would be and theta is between negative pi over 2 and pi over 2. And now I go back to your trig class and I say, let's draw a picture of the unit circle, right? Because when you learned about sine and cosine in your trig class, they taught you all about this, right? And so where is 5 pi over 6? Well, 5 pi over 6 is almost 6 pi over 6, almost pi. So it's pointed this direction, right? There is 5 pi over 6. And if I ask what's the sine, I have to know my points. This point here has coordinates. I guess it would be negative radical 3 over 2, comma, positive 1/2. I remember memorizing those unit circle points. About to do that in my pre-calc class today, actually, or tomorrow. What's that? Now you can see, right? Because we know, because the range is from negative pi over 2 to pi over 2, it's either we're here or we're here. And so, like Mike said, I could see right away, this corresponds to right here, pi over 6. Or maybe it should be down a little more. But the point is that point there, right, pi over 6 is the same as 5 pi over 6, because this would be radical 3 over 2, comma 1/2. And so, in particular, yeah, all you care about is the sine, right? The sine of theta, equals that 1/2. And so now I can see that theta has to be pi over 6. Okay? I really believe that in calculus, as you go through Calc 2, if you guys continue this habit, anytime you see an inverse trig function, call it theta, then write a regular trig equation, and draw a picture, you really simplify your life in terms of dealing with these. Because you guys know a lot more trig than you give yourself credit for sometimes. You guys have learned a lot since you started. So any questions so far? Yeah, Ashton?
So would 5 over 6 be wrong for that answer?
Oh yeah, it would be wrong.
It's not in the
It's not in the correct range. Matter of fact, if I take my calculator, got it? Yeah. Let's see what the calculator would say. Just curious. If I say inverse sine of the sine of 5 pi over 6, what does it tell me? That. You might say, well, that didn't tell me much. Well, let me multiply that by 6, because I'll be clearing out the denominator. You guys recognize that one? That's pi. So it shows you had pi over 6 in the calculator, not 5 pi over 6. Okay? All right, so let's move on. You guys try this one. The secant of the arc sine of square root of x. Well, maybe I should show this one, actually. But you might have an idea of how I start, right? The strategy I'm suggesting is, anytime you see an inverse trig function, that's what you're going to turn into some Greek letter, right? So here I go. I'm going to let theta be the arc sine of the square root of x. And immediately when I do that, right away what do I write next is a regular trig function. I write Yeah, Jeff? Sine of theta equals, well, what? Now forget secant for a minute. Oh, I see what you're saying. Over here, you're right. This, we're saying, is becoming theta, right? So basically, the problem said, find the secant of the arcsine of radical x. Now I could say the problem says, basically, find the secant of theta. Okay, that's what it says. But over here, when you write theta is the arcsine of square root of x, the next thing I want you to write is that the sine of theta is equal to what? Square root of x. And you might say, well, how did that help me, Paul? But what I'm going to tell you is, if you write this part as a fraction, you'll be happier. And how do I write square root of x as a fraction? Well, I can always do this, right? You can put it over 1. So the sine of theta is equal to the square root of x over 1. And now I'm going to go back to my trig class where I used to draw right triangles. Right? And I'm going to put my theta, my angle, right here. And so if I tell you that the sine of theta is the square root of x over 1, what's that look like on the right triangle? Yeah. This is square root of x from my SOHCAHTOA days, right? And where's the 1 go? Right there, hypotenuse, because it's opposite over hypotenuse. So really, theta is very simply the angle in that picture. Does that make sense? Well, I guess it, okay, let's put it this way. This is going to be good enough. And I'll show you very precisely what we mean in just a second. But when I say this is good enough, see, the fact that I drew those two expressions on my right triangle, I can figure out the third, right? So let's do that. How do you figure out the third expression? Well, you call it b or something, right? And we do good old Pythagorean theorem, right? So I'll say, yeah, a squared, which is square root of x squared, plus b squared, right, is equal to what? Sure, because it equals 1 squared, right? That's the Pythagorean theorem. So I get x plus b squared is 1, and so b is equal to the square root of 1 minus x. I mean, to be accurate, it's plus or minus that, right? Well, let's see. For now, let me just write square root of 1 minus x, and I guess I'll keep the plus or minus in mind. And I'll show you exactly what I'm talking about in a second. But basically what I have to do now is I have to find the secant of theta, right? Well, to do that, look at the picture. Because secant means 1 over what? Cosine of theta. Cosine of theta would be b over 1. But 1 over the cosine of theta, this would be 1 over b, which is the square root of 1 minus x. Right? I mean, you could argue this. I know that cosine of theta is adjacent over hypotenuse. So when I'm doing secant of theta and I say look at the picture, I know that secant of theta is equal to hypotenuse over adjacent. One way or another, you got to come up with this, guys. From the picture, get that it's 1 over the square root of 1 minus x. Oh, one other thing. I could argue that it's plus or minus that. Why? Well, same reason I had a plus or minus here, and also because, look at the original problem. The original problem, we were finding something about the arc sine. Well, the arc sine, remember the range could go down to negative pi over 2. And if it's down in there, you're taking the secant of a negative number. Okay, so. But this is the idea. You guys understand the strategy? This will come in play a lot, both in Calc 1 and Calc 2, this kind of trig mechanics that we're doing here. All right, so we haven't really done any calculus yet, but I think that was important to review with you guys. So let's see what we can do now. Well, for example, maybe I want to find the derivative of the arctangent. So basically, we're going to come up with a few new derivative formulas today for these inverse trig functions. They're especially important in Calc 2. So, how do I take the derivative of an inverse function? Well, one way actually is the inverse function theorem. We have that. So I could just kind of employ that. But I'm going to show you another way that the book uses, which I think in some ways is smarter because it reflects what we just did. Okay? So I said y equals the arctangent of x. That's what I said. Well, as soon as you have an inverse trig function, I like to write a regular trig equation. And so I'm going to write x is equal to the tangent of y, right? Or the tangent of y is equal to x. I guess you could write it either way. Maybe I'll write it the other way. Tangent of y is equal to x. And now, what I'm going to do is a trick we've learned before. It's called implicit differentiation, where I take d dx of both sides. How does this work? Okay, derivative of the tangent of y would be secant squared of y times y prime, or dy dx. That's the chain rule. That's how implicit differentiation works. Okay? So what do I get now? That equals what on the right-hand side? 1. Okay. So y prime equals what? 1 over secant squared of y. Hey, what's 1 over secant squared of y? You could do better than that. Because secant is a reciprocal, right? Of what? So this is just cosine squared of y. Now, I don't quite like this formula because it has y prime and y in it, okay? But we can do better if we have the idea up above. Not only should I write a trig equation, but I also should draw a picture. I didn't do that. Maybe I should have done this down below, because usually I write the picture on the right. All right, well, let's do the picture on the left. Here we go. So what's the picture look like? Well, I think, let me ask you first of all, what's the angle in this problem? Is it x or y? The angle is y, right? I'm taking the tangent of y. Okay, so let's draw my right triangle. So this is kind of interesting. I'm going to put a y here instead of a theta. And that y is going to be the angle. So again, what I wrote was tangent of y is equal to x. Oh, but how do I write x as a fraction? X over 1. So where do I put those things on my picture? Opposite is x. Jason is 1. See if you guys can give me the hypotenuse here. Well, that would be what? Square root of? How about I write 1 squared plus x squared. Does that make sense to you guys? That's the Pythagorean theorem. I mean, you could work it out. X squared plus 1 squared has to equal that squared, and it does. Okay? So once you have this piece filled in, right, we compute that. Then I can simplify this expression a little bit more. What does it say? It says y prime is, I know it says cosine squared, but remember what that really means is the cosine of y is being squared. I'm going to emphasize it this way for a second because I think it kind of tells you what's going on. What is the cosine of y? From the picture. Again, look at the picture. Look. Here, emphasize it. The eyes are looking right at it, right? All right. Look. What is it? So for the cosine, it's adjacent over hypotenuse, right? So this is equal to what squared? 1 over radical 1 plus x squared. And so I get 1 over 1 plus x squared. Cool. The derivative of arctangent. You guys, by the time you're in Calc 2, you know how I noticed that you guys did successfully memorize the derivatives of the 6 trig functions? Well, there's something else that you have to have memorized. You have to know the derivatives of the inverse trig functions. So that if I give you this, by the time you're in Calc 2, you're not going to draw all this and work it out that way. You're just going to know y prime is equal to what? Done. 1 over 1 plus x squared. Because we already did it. Now, if you're ever stuck, you know how to work it out. Okay? But I'm telling you that this is an important derivative. So how many important derivatives are there? Well, here they are, right? The back of your book has the important derivatives. And how many do you already know? Well, okay, general formulas. Do you guys know these first 8? I think so, right? Here, let me zoom in. It's hard to see. Yeah, let's see. Derivative of a constant is 0, no problem. I can ignore a constant in front, no problem. Adding, I do them separately. Subtracting, I do them separately. Multiplying, can't do them separately. Got the product rule. Dividing, quotient rule. Ho di hi minus I di over ho ho. Bing, bing. Where's the bong? That's the chain rule, right? Ding, dong. You guys know those. Nice job. You know the derivatives of the 6 trig functions? You sure needed to know them for problem 1B on your exam, didn't you? All right. Next. These 6 inverse trig functions, we know how many of these? Really? I think we only did 1. Which one do you know?
You're right.
Inverse tangent. But Jeff's right. We actually know 2 of them. He noticed, it's quite observant of him, that really you only need to know these 3. Because the inverse sine, the inverse tangent, and the inverse secant. Because if you know those 3, you get these for free, you might argue. Because Jeff noticed, what's the derivative of the inverse cofunctions compared to the inverse functions? Just a negative in front. So when Jeff said that we know 2 of them, this is probably what he was thinking about, which is very impressive. Very observant. Pretty cool. Oh, wait. You guys know these, too. What's the derivative of e to the x? What's the derivative of natural log of x? What's the derivative of 3 to the x? Well, it's 3 to the x times the fudge factor, which would be, there it is, natural log of 3. You guys know a lot of calculus.
What's left of Calc 2?
What's left for what?
Calc 2.
Of Calc 1 to get ready for Calc 2? Yeah, I mean, we may as well stop now, right? Well, I guess we have to work with these inverse trig functions. And then what about hyperbolics? Well, I'll tell you what, guys. You don't need to memorize the hyperbolic trig functions or the inverse hyperbolic trig functions. In the old days, you did. But now we got soft here with the millennials. No, it's true. No, I didn't know these either. I just knew, well, I'll show you guys what these are maybe at the end of the year. They're cool, but yeah, this is enough. If you guys get that far, that's all the memorizing you need. Well, and you better know how to do a few things, I guess, right? We better know how to take derivatives and how to take antiderivatives. All right, so we need more examples. So that's why we're here. Here we go. Boom. Try that one, guys. Y equals the arc sine of x over 4. Oh, I wish I still had that formula sheet up. Should I give you the formula? Sure, why not? I mean, we could prove and derive the formulas, but I feel like one's enough for this class. All right. We did one. The other two are done basically the same way. I think the arc sine one might be worked out in your book. So let me give you the formula, and then you just apply everything else you know. That's what the homework's going to be like, you know? So what's the new fact that I need about arc sine? I need to know what its derivative is. So let me tell you. Derivative of the arc sine of x is equal to 1 over square root of 1 minus x squared. It's funny. It's a lot like the arctangent, which might not surprise you. What are the differences? Yeah, this one's a minus instead of a plus. And what's another important difference between arctangent and arcsine? There's a square root in the arcsine. In the arctangent, because you got this cosine squared shows up, you don't have that. All right. All right, so let's play the game. How do we do this? Find the derivative. Y prime equals, it's easy. It's just 1 over square root of 1 minus, but I'm not going to write x. What am I going to write? What? X over 4. Yeah, we're taking the arcsine of x over 4. So I'm going to put an x over 4 here, squared. Am I done? Dong! So times the derivative of what? This is the chain rule. Well, the derivative of x over 4, right? So you got to multiply. So what are we really multiplying by? What is the derivative of x over 4, guys? Come on, you're on video. Make me look a little better. What do you have? Television audience at home already has this done. Derivative of x over 4. 1 over 4. So it's 1/4 times this stuff. 1 over the square root of. Now, can this stuff be simplified? Well, if you were going to start simplifying, where would you start simplifying? Yeah, down here, this x over 4 in parentheses being squared, how could I write that? I could write it as x squared over what? 16. And if you're going to do that, then I suggest we rewrite the 1 also. Because if I want to subtract these fractions eventually, how should I write that 1? 16 over 16. And that's really kind of cool. So y prime so far is this, but watch what happens. I get y prime is equal to, and I'm going to point out that you could, if you wanted, write this as 1 over, instead of 4, I could write that as the square root of 16, which I think is kind of interesting because now, if you do subtract these fractions, underneath you have 16 minus x squared over 16, right? And you might be able to see how the square root of 16s are going to cancel. And so I think the back of the book would probably put this as their answer. 1 over the square root of 16 minus x squared. And you might be wondering, well, how'd they get it? But do you see it now? Yeah, Garrett?
Did you just take the
When I multiplied, yeah, exactly.
And that's why you just have the radius is minus.
Yeah,
Okay.
that's right. So I think this is what we would put for the answer to the derivative of the arc sine of x over 4. Okay? So it's 1 over the square root of 16 minus x squared. So, let's move on to another example. Oh, well, that's it for derivatives, which is great. I mean, the reason you study inverse trig functions at all is not so much that we just want more derivative formulas. The reason you study them is because they become very important when we want to talk about how do you integrate different types of functions. And so I would argue that this is the real reason to have this section. It's all about integration. Okay? I mean, suppose I say I want to integrate this function. Take a look at this definite integral. You know, before today, you'd have no chance at this. None. Because how would you possibly proceed? What's the function that I'm looking at? You know, I wrote it this way, but you guys do understand that's the same as this, right? Integral 0 to 1, 1 over 1 plus x squared dx, right? So, yeah, you actually know the antiderivative if you followed today's lesson. But without that, like, you know, you can imagine someone might try substitution. What would you let u equal if you were going to try substitution? Well, maybe someone would try 1 plus x squared. Not a bad move. And then what does du equal, though? And so why doesn't this work? What's the problem here? We don't have that x. So it's not going to work. Bless you. So, luckily, we remembered one of these derivative formulas, right? Just on the last page, I said, oh, that function, that's the derivative of what? Of the inverse tangent, right? And so I guess immediately, because you're going to know those for Calc 2, you're going to say, oh, that's the arctangent of x, hopefully, from 0 to 1. But it does get more difficult than that. It's not just instant recognition sometimes, and sometimes you have to do some manipulating to get it to look right. I'll show you that. So let's see, what do? We have the arctangent of x. And so I guess I would need to do the arctan of 1 minus the arctan of 0, right? And actually, this is a worthwhile exercise, so I'm going to pause the tape while you guys finish the problem and review a little bit of your tangent trigonometry here in the meantime. So, arctangent of 1 minus the arctangent of 0. I mean, basically, I guess I need to know a few things like, you know, what does the tangent graph look like? The tangent of x. Y equals the tangent of x. Well, that's this kind of graph, right? Maybe that's what I think of. Or maybe I'm a unit circle guy, right? And so the unit circle looks like this. And so if I want the, you know, when I see this, I'm thinking, call this one alpha. Here, let's call this alpha minus beta. And so basically, I'm saying here, the tangent of alpha is equal to 1, and the tangent of beta is equal to 0. Well, what angle do I want to get 0? That's 0. Because if you look on the unit circle, right, there's my sine and cosine and sine, and 0 over 1 is 0. So that's the tangent of beta equaling 0. This graph goes right through 0. Now, where does the tangent of alpha equal 1? Pi over 4 is right. Because at pi over 4, on the unit circle, you have the sine and cosine are equal. And so that's why the tangent of pi over 4 is 1, the tangent of negative pi over 4 is negative 1, and then, of course, at pi over 2 and negative pi over 2, you have the asymptotes. Then it repeats. But this is the only piece of it that I use for the inverse trig function. Okay, correct answer is pi over 4, which I could do on a calculator, I guess, and get an approximate answer. Any questions so far? Curtis.
On the problems with 4,
Yeah.
how do you know where to put the 1?
Where at?
When you drew the triangles.
So, yeah, let me show those. That's a good question. Back when we did this problem, first one we did was with the arc sine. So I wrote sine of theta is square root of x. I just wrote it as a fraction. So you always put it over 1. But I guess your question is, how do you know where to put it in the triangle, right? So what do you know about sine? Sine is opposite over hypotenuse, right? That's why the 1 was the hypotenuse. But what about the tangent? For the tangent, it's opposite over what? Adjacent. And so that's why the 1 was the... Here, y is the angle and 1 was the adjacent. Does that make sense? Good. And then we moved here. Let's move on. Try another integral. Drawing those pictures is going to keep coming up. Let's see. All right. This one, not so nice. Because I don't immediately know a derivative that looks like that. But what does this one kind of look like? Kind of looks like arctangent. Good. If you can recognize that, then you can do the problem. You say, wow, it kind of looks like arctangent. Maybe I can do a substitution to get it to look exactly like the arctangent. Okay? So let me demonstrate it for you. I'm going to let u equal, you have to think of doing this, I guess, 3x. Why did I say 3x? Well, because this is really 1 over 1 plus parentheses 3x squared dx. Do you guys see that? So I write down u equals 3x, and then right away I need to compute what? Du is equal to, bless you, 3 times dx, right? Do I have a 3 dx? No, but I can get it, right? So this integral is equal to, when I change to the world of u, 1/3 the integral of something du. Does that make sense? Again, because to get that 3 there, I need a 1/3 also. That's kind of in my mind. The 3 dx is going to become the du. That's okay? All right. So now what do? Well, what do we have here? We have 1 over what? 1 plus u squared. Got it. Should be able to finish now, right? Because what's the antiderivative of 1 over 1 plus u squared du? We learned today it's the arctan of u. That's the whole reason we wanted to study it, is that there's lots of times that you want to integrate. and your final answer is an arctangent. Actually, I remember studying integration in Calc 2, and I will tell you that arctangents come up a lot and logarithms come up a lot. Those things just come up a lot in calculus when you're doing integration. So let's see, we get 1/3 the arctan of what? Of 3x plus c. That's the answer to the original problem. It takes a little work. Here's the next one. Would you believe me if I tell you this one is not an arctangent problem? What do you think it is? It is. It's an arcsine problem. Yeah. Now it's not it's not perfectly in the right form yet. Okay. So you kind of have to know what to do here. Like, what do I let u equal, etc.? So, okay, couple things you can do. I mean, first of all, you can look in the book and you could say, well, do they give me a formula? And the answer is going to be yes, they give you a formula. Let me show you. Because they did derivatives, and now they say integrals. Boom. And they say, ha, here's the derivative of sine. And so, because of our work, you're going to notice something in these three formulas that was not present in the derivative formulas. And what is that? What do you see that's different here? The A's. And I haven't mentioned the A's at all yet, okay? But if we go back to the last problem and said, oh, I want to apply that middle formula number 2, why didn't it come up at all in the last problem? Well, because what was A in the last problem? A was equal to 1. And that's why, if you look at the formula, it's just 1 times the inverse tangent of whatever x is. And our x got replaced with 3x, basically. Okay? And it's fine. But I'll be honest with you, memorizing formulas is not the fun part of mathematics. It's not. We want to learn technique. And so I'm going to introduce to you to a technique that's really a Calc 2 technique, okay? And just show you how it works for this problem. Then I'll show you could also just apply the formula, and then you kind of decide what's easier for you, okay? So it all comes down to recognizing what you have. This is an arc tangent problem, whereas this one is what kind of problem? Inverse sine, right? So watch what I'm going to do. Here's the technique at work. I'm going to let theta equal the arc sine. And here's what you have to do, though. You have to let it be x, which is this thing being squared, divided by 2, because that's what this is being squared. X over 2. Write that down, guys. Let theta be the arc sine of x over 2. I want you to write that down, because as soon as you write that down, well, we should compute d theta as well. No, not so fast. Let's do this. Let's turn this into a regular trig equation. So if I turn it into a regular trig equation, what's it going to say? Sine of theta is equal to what? X over 2. Can you draw a picture of that? You can. What would it look like? Well, it would look like this. And Curtis, this really ties into your question, so let me ask you now. If you're looking at this equation I just wrote, sine of theta is x over 2, where do I put the variables on the picture? 2's on the hypotenuse. That's right. X is the opposite, so it's x over 2. Okay, see that? No? The sine of theta is equal to x over 2. So again, we know that sine is opposite over hypotenuse, and so that's where these x and the 2 come from. Garrett?
When you let theta equal arc sine of x over 2, how did you determine the x?
Now that's the good question, okay? And what it really comes down to is, if you look at their formulas, they say the final answer is going to be the arc sine of x over a. You see that?
Yes.
Well, the a is whatever's being squared on the left, and the x is whatever's being squared on the right. So for us, I looked at it, I said, well, it's got to be 2 and x. Okay? All right. Hey guys, if I filled in 2 parts of a right triangle, I ought to get the third for free using Pythagorean theorem. So I use the Pythagorean theorem and I get the square root of 4 minus x squared. Is that okay? A little geometry going on? So I worked that out. That may come in handy. Now, here is where it's funny. I don't think the book will show you any of this yet. But I just think it's smart to show you now. You're going to need it eventually. What the book might do is they might say this. Hey guys, we're going to let x equal 2 times the sine of theta. And it's funny. I don't know how the heck they do this. They skip all this. And they basically just say, oh, look at that problem. X is 2 times the sine of theta. To me, if you skip this, you're not showing where it's coming from. We're doing theta is an inverse trig function. That's really the substitution we're making. And we work it all out. And basically, I took this equation here, and what did I do to both sides of it to get that? Yeah, I got rid of the fraction by multiplying by 2. Are you with me? My reason for doing this is now I want to write out what dx equals. That's not hard. What would dx equal? If x is 2 times the sine of theta, what is dx? 2 cosine theta d theta. 2 cosine theta d theta. And so, here we go. We're going to do our substitution here. We're going to take this integral, and we're going to rewrite it now, okay? It's really beautiful what happens. Watch. Integral, where it used to say dx, we're going to write 2 cosine theta d theta, because that's what the dx is. We just worked that out. The other thing is a big fraction. I'll do the numerator. 1. You guys do the denominator. Well, where does the substitution happen? I guess there's a square root, and then there's a 4 minus, and then there's stuff squared. Now, what goes in that parentheses? Not x anymore. What am I going to write? 2 sine of theta. Okay? So, here I go. This equals integral 1 over square root of, let's simplify those parentheses. So I get 4 minus 4 sine squared theta. And up here I have, are you guys okay if instead of writing the 1 on top and this stuff after, could we change this and just write 2 cosine theta d theta? Is that okay? Just trying to make it go a little faster here. And one of the reasons I wrote it this way was I noticed I have a 2 up top, I have a cosine of theta, I have a d theta. And then on the denominator here, I notice that I have the square root of 4 times the square root. If I factor that 4 out, what do I have left? 1 minus sine squared theta. Do you see anything that cancels? The 2 and the square root of 4 are the same, right? So those are gone. Do you notice anything else? Well, what I have is I have the square root of, what is 1 minus sine squared theta? It's cosine squared theta. Right? So what happens? That's beautiful. It all cancels, right? Because cosine is the same as the square root of cosine squared if things are positive anyways. And so what you end up integrating, I guess, is just 1 d theta. Okay. So I integrate 1. What do I get? X. Well, not x because it's d theta, so I get theta plus c. But what was theta? Theta was, there it is. So the final answer would be arc sine of x over 2 plus c. Now, I'll be honest with you. Could I get that original answer from my formula? Well, yeah, right? If you wanted to get it from the formula, here's what you do. You look at this problem. You say, okay, a is equal to 2. And what I'm doing really is I'm using formula number 2 from the book. And so the answer should be just arc sine, no, formula number 1 from the book, right? Yeah, formula number 1. So the answer is arc sine of x over a, which is arc sine of x over 2 plus c. So if you recognize the formula, you don't need all this. But in Calc 2, you'll need all this. So I may as well start showing you now. It's kind of where we're at, where I'm at anyways. Okay. Oh yeah, so I only have 2 more examples left in class. This one's tricky. I don't know, I'm going to pause for 1 second. Okay, so I only have time for the last one of the last 2 problems. Let me show you the last problem just because I want to show it to you. It's a little bit different. Let me just say that this one, if you get something like this on the homework, is an inverse secant problem. You can recognize it for 2 reasons. Number 1 is there's an extra x outside of the square root. But the second thing is because the x squared minus 1 instead of 1 minus x squared, it's the order that you have. This signifies inverse secant. And the cofunctions we're not going to use for integration. Because remember, they have the same derivatives just with a negative sign. Just never will happen. All right, but let's go back to this one. This one is a classic Calc 2 problem. They say integrate this, and you're like, what? It doesn't look like any of them. Well, you have to make it look like them. And so I'm going to work through the details with you. And that's going to end class today. So here I go. What you do is you write this is equal to 1 over the square root. Now I'm going to do this. I'm going to write this as the square root of, oh, and there's a dx here. I don't know where it went. Put it out here. So I'm going to write this as -1 times stuff. This is all happening under that square root. So what would be the stuff if I factor out a -1? Well, it would be x squared, and then it would be minus 4x. And you'll notice I left some space Because what do you think I'm going to be doing here? Completing the square, absolutely. You want to complete the square on a problem like this. So how does that work? I do half of negative 4 squared. Negative 2 squared equals 4. So what I do is I add 4 here, right? Here, let me do that in the next step. It's getting a little messy. So this equals integral 1 over square root of negative 1 times stuff, x squared minus 4x. Now what I just worked out is that I should put a plus 4 here. Are you with me? But you can't just put plus 4. You have to compensate for it. So what else am I going to write? Well, of course, I'm going to write plus 4. What? Well, because, let's see if you understand this. I didn't really add plus 4 in blue. I added 4 times negative 1. You see that? There's a negative 1 factored out here. So you really added negative 4, and that's why you need to put a positive 4 there. Does this make sense? Try the next step. Oh, I'm almost out of time. 1 over square root of. Here I'm going to write the 4 here. And then minus. And what did that completing the square thing become? It became x minus 2 quantities squared. Okay? And since I'm out of time, I'm just going to apply the formula instead of doing all that other stuff I showed you. The formula would be arc sine x minus 2 over 2 plus c. Because that's the u and that's the a. The a is 2. All right. Hope you enjoyed it. We'll see you guys.